this lecture. I'm very happy to introduce Miss Yisan Liu and Mr. Panda. He said you can call him Panda. Okay, to talk about the hydrogel-based tribal electric nano generator for mechanical engineering, harvesting, and motion detection. Okay, please join me to welcome them.
So, okay, and due to the human health awareness increase and also the big data increase. So in here we can see that the wearable technology application also increased from 2050 to 2026. The wearable markets increased a lot. So it means the units that sold also increase. So we will ask what kind of the wearable technology we have and what is there any device. So the device, for example, we can see that we have the smartwatches, fitness trackers, smart shoes, and etc. This device can detect our human parameters. And for example, for the medical application, the doctor can use the wearable device to detect the patient's heart pressures, heart rates, and etc. So it makes doctor more easily to know the patient's situation. And also for the fitness application, we can know the calorie we consumption and also know the position we do. So it means this wearable device can make our daily life more easier and convenient. And also the wearable device can connect to the Internet of Things. So we can try to calculate data and analyze automatically to and connect to other devices. But this kind of wearable have some drawback because nowadays we try to make the wearable device become small and mobility and also multifunctional. But the device we always use are conventional batteries. So in here we can see that the drawback for the first part is the battery is bulky and heavy. So if we put in our hand for a long time, there is a marking on our hand. So it means it's not appropriate for the flexible portables. And the second part is that in the device, we can also see the percentage of the batteries remaining. So it means we need to pay attention about how many batteries we have. So it means the battery have the limited lifetime. We need to recharge and also we eventually we still need to replacement the batteries. So we will have the pollution problem because inside the materials there is a lot of taxes. So we need to pay some money to deal with the taxes material. So it means we still need to find other other electricity resource and that is clean and also continuous. And also in our world electricities, we are relies on the thermal powers. And the thermal powers is from the conventional energy sources. So what is the conventional energy source? It's like a coal, oil, or the natural gas. And this we can call that it is a fossil fuel. And it has been explored and be used for the power generation in power plants through the past few centuries. So in here we can see there is a lot of kind of the conventional source of energies. And also here is the thermal powers. And we can see that when we are using, it will emit the carbon and other greenhouse gas here. So we try to find other new energy resource. So here is the renewable energy source and what kind of the energy resource we have. there is a bioenergies, solar energy, geothermal energy, wind energy, and also the hydropower energies. And this kind of energies is limited resource. And here we can also see that the hydropowers is the highest proportion compared to any others renewable energy resource. But even we use the renewable energy resource, still we have some challenges we facing. For example, the hydro energies, it is intermittent, so it means it is not available during night or when the weather is not good. And for the wind energy, there is a big turbine here. So when they are rotating, it will create a lot of noise. And also when the bird fly away, and it will the turbine will kill the bird. Also, the bird will getting hurt. And the third part is hydropower. We need to struck the bar on the rivers, and this kind of situation will destroy the ecologies and also change the temperature for the for waters. So it means we still need to try to find other the resource energy resource, and it is the clean and also continuous. So before I talk about triple electric nanogenerators (TENG), I would like to introduce about the inventor. And he is an inventor, Zhongling Wang, and he is now teach in the Georgia of Technology universities. And in here we can see that he used the triple electric nanogenerators try to create the electricities, and this electricity can like the LED lights. And there is a lot of different application potential for the TENGs, like the micro nano energies, self power sensing, high voltage power supply, and also the blue energy. So here, there is the application for the blue energy. They put the TNG in the ocean, and also we can try to put this device in our human bodies. So you can see that it can try to have the signals and also can convert the energy into the electricities. So before I talk about the working mechanism about TNGs, I think if I directly talk about contact electrification and electrostatic interaction, you will get confused. So I will first talk some examples. What is the electrification? It means when we take the plastic ruler and the fur together, and when they contact together, one part will become the positive charge and one part will be the negative charge. So the TNG is like these principles. The working mechanism is about the contact electrifications and the electroinductions. So it can convert the mechanical energies into the electricities. So what is the mechanical energy source? So for example, when we have the body movements, we have the vibrations and also like a wind vibration. This kind of the resource is like the mechanical energies. So TNG can translate these energy into the electricities, and these electricities can try to make some small device have some power, like the earphone or the watches. So here we can also see that due to the contact electrifications and the electrostatic interactions, it will create the electron potential. This due to the electron potentials, we can change that we can get the electricities. And the TNG have the advantage is that the material we can choose that is flexibility materials, and also TNG is self power. So it means TNG is very suitable for the wearable device. And there is a lot of different mode for the TNGs. And first one is a contact separate mode. Second is a relative sliding mode. Third one is single electron mode. And the final is the freestanding mode. So in here, we can see that there is the green part is the triple electric material one, and the second part is the triple electric material two. So it means when we contact together, the green part will induce the negative charge, and the blue part will induce the positive charge. So when they contact and separate, it will create the electron. It will have the electron potential. So the electron will try to change or release from the electron. And for although here is four different mode, but we will focus to the contact separate mode and the single electron mode because these two modes is more common use. So here I will try to compare the vertical contact separate mode and the single electron mode. For the vertical contact separate mode, although it is a well-known type, but when we have the package, it is difficult because there needs some spring and also needs the volume for the varying gap. But compared with the single electron mode, you can see that the structure is more simple, and also the more important thing is that because we need two material. One part is the positive, and the other part is for the negative material. So our human body, our human skin can directly to use become a positive triple electric surface. So the single electron mode is more easy for us to become the wearable device. So what is the working principles about the single electron TNGs? And for the top is our structures. And here we can see that the electron will be in the middles and the stolen layer, and there is also the triple layer. So in the first step, we can see that the turbine layer and the stolen layer, they touch together. So in this time, it will create the contact electrifications. So it will try to create the negative charge and also the positive charge for the triple layers. And when we try to release, so they will try to have the electron inductions. So the positive charge about the electron will induce to the surface due to they need to have the balance for the electron. So in here, the electron will try to release to the ground. And in the third step, when it completely separates, it will become the electrostatic equivalent. And the final step is that when they press again, so it will also induce the charge, and in this type, the electron will go back. And this process will continuously. So it means the electricity we get is the alternative current power. So in here, we will try to find some material to put in our TNGs. And the material we choose, we will choose the hydrogels. And compare with the traditional TNGs, because in here, we will focus on the electron. And the electron needs the conductivities, and metal have the high conductivities. But the drawback is that it have the limited stretchability. So it means when we do the contact and separate, the effective contact area is limited. But compared with the hydrogels, hydrogels have the several properties. The first one is the transparencies. Second is excellent stretchability and deformability. And the third part is the environmental adaptability and biocapability. So in here we can see that the hydrogel can directly put in our human bodies, and when we are bending, it can also get the different signals. So, what is the hydrogels? The definition about the hydrogel is that it is a 3D dimensional hydrophilic polymer network, and it can contain a lot of waters, but it will not dissolve in the water. And this is the graph about the hydrogels. So, what kind of material can become the hydrogel? We will use monomers and cross-linker and also the initiators. And here will be the waters. So that is the hydrogels. So here is videos to introduce about what is the hydrogels. And also the second video is for hydrogels.
Decades, researchers have been in pursuit of a long-expression hydrogel. Medical approaches to repair, replace, or regenerate damaged tissue are exploring the use of these materials. Artificial tissues need to withstand stress and a wide range of motion. Although some hydrogels have met the demand for this, most aren't durable. Eventually, they become stretched out and unable to return to their original shape. A group of researchers at Harvard decided to tackle this problem by manipulating the underlying structure of hydrogels. Hydrogels consist of long, chain-shaped molecules made of repeating units called monomers. These chains connect to each other and provide mechanical reinforcement through crosslinks and entanglements. Entanglements are physical connections where chains weave around each other like tangled spaghetti noodles. Most hydrogels only have a few entanglements along each polymer chain. The structures appear like a net with wide gaps that become swollen with water. Crosslinks are chemical bonds that prevent the hydrogel from dissolving. If more crosslinks are added to the network, the hydrogel becomes more rigid and brittle. Polymer segments between each crosslink become shorter and easier to break under stress. In contrast, increasing entanglements makes the material stronger and tougher, as the chains can tug on each other when they cross, but still have the freedom to slip without breaking. In this study, scientists set out to create a hydrogel with lots of entanglements, but few crosslinks. Hydrogels are all made of similar ingredients: monomers, initiators that link monomers into a chain, crosslinkers which connect the polymer chains to one another, and water as the solvent which disperses the ingredients. Most recipes require a lot of water. For every molecule of monomer, there are many of H2O. The researchers created a highly concentrated hydrogel by using a different ratio: 2 water molecules for every monomer. This approach slowed the polymer growth to create long polymer chains with almost 100 entanglements along each path. The microstructure appeared more like a dense fabric than a fishnet. After saturating the entangled hydrogel in water, researchers tested how the material performed compared with traditional hydrogels. The highly entangled hydrogel could lift a weight, while the other two both tore. The new hydrogel also bounced back to its original shape after stretching, unlike previous tough hydrogels. The scientists say these qualities make the durable hydrogel a great candidate for a host of applications, such as creating the surface of an artificial joint. Since this material can be made with the same ingredients as traditional hydrogels, the researchers hope to see their stretchy and strong material used in ways they haven't yet imagined.
So,
Scientists have developed
and also, hydrogel has a lot of kind application, and this video is about the application for hydrogels.
injectable gel touches the various soft tissues in repairs caused by accidents or traumatic shocks.
So if you're practicing some sport like ski or football, you may face some injuries, and in that situation, you will need to go to the hospital so that the surgeon may try to treat your torn meniscus or cartilage by using sutures. And that would not be ideal because in that situation, you will basically punch your tissue. So it would be much better if we would have a glue that will help in the healing of your tissues.
For years, scientists have been trying to develop soft tissue adhesives that can withstand the mechanical stresses of the body. Now, researchers at EPFL's Laboratory of Biomechanical Orthopedics have successfully produced an injectable biomaterial that sticks to different tissues.
We have designed a family of injectable hydrogels that are intrinsically adhesive to various soft tissues and can be used for the treatment of lesions in the body. So based on this system, we fabricated different polymeric backbones, which we can make new hydrogels with them, with available adhesive sites and the capability to form hybrid networks. What is interesting with this hydrogel system is that when it's injected, it's in liquid form. Then a light source hardens the material and creates adhesion to the tissue. Our system presents a wide window of physiochemical properties without affecting the adhesive characteristics. This is particularly important for the application which needs superior material properties.
An additional advantage of this hydrogel is that it can include drugs or even cells that promote the healing of damaged tissue, such as cartilage that does not regenerate spontaneously.
So if you have a gel that can be injected and can attach very well to soft tissue, then you have a lot of clinical applications that you can target. And we target specifically application in the knee for the soft tissue, either cartilage or meniscus. And we received an Swiss grant to translate basically this discovery in the lab into a clinical application.
Dominique Violetti hopes that this hydrogel will be available on the market within 5 years.
Okay. This one. And also, this also application for the cell phone. So in this video, we can see that the hydrogels contain the stretchability. So there is a lot of different kind of application, like the wood dressing and contact lens, the drug delivery and the diaper, and also for the agriculture and the tissue engineering. But even we choose a hydrogel to become the electro, but not all of the hydrogels that contain the ionic conductivities. So there is several strategies to increase the ionic conductivities for the hydrogels, because the hydrogels in our case need to have the hydrogel is be the electro, so it means it need to have the ionic conductivities. And the two strategies, the first one is try to add the conductive materials. And the conductive material is like the PPY or pennies or the graphite. And the second part is try to add the inorganic salt. And the organic salt is like LiCl and ACl. But there still have some drawback if we try to add these kinds of material in the hydrogels. Because for the conductive polymers, it is easy to aggregate due to it will impedance the conductive percolation network. And the second is that due to the structures is hydrocyclic, so it will limit the flexibility about the hydrogels. And the third part is that this kind of conductive polymer is the color that have is black or dark blue. So the hydrogels we get will don't have any transparencies. And for the inorganic salts, due to the weak bonding between the water, so if we use this kind of hydrogels and put in the room temperatures, it will have the evaporate issues. So it will shorten the stability. So in our case, we try to we try to add the ionic liquid in size. So what is the meaning about the ionic liquid? In here, we can see the structures. It contains the cation and anions. And these pictures is about different kinds of cation and anions. And because ionic liquid contains the high ionic conductivities and also these kind of the properties. And also there is a lot of different application for the ionic liquids. So if when we use the ionic liquids, and there is two types of gel we can get. The first part is ion gels. So what is ion gels? In this picture, we can see that the ion gels is they only add the ionic liquid and the polymers. But we can see that in this table, there is different kind of ion gels. The ionic conductivity is not high because if we only add the ionic liquid, it will have the high viscosities and increase the transmission resistance. Also, it have the low diffusion coefficient. So in our case, we try to add the water inside. If we add the water and ionic liquid together, we will have the binary solvent. And these hydrogels can also have the properties like the ionic liquid. And also, the water will have the strong interaction with the ionic liquids, so it can suppress the water freezing and also evaporate problem. So it can increase the stability if we put in the room temperatures. And this is the material we choose. Our monomer is AA and DMAPS, and the ionic liquid we use is ENIMBR. So we can take a 10 minutes break. Yes.
Hydrogel that incorporate ionic liquid inside hydrogel. So there are two strategies to make or fabricate ionohydrogel. One, you fabricate the hydrogel first, then dip into the ionic liquid. And another strategy is to mix together and forward for the chemical reaction. So we proceed towards the reaction like mix together and forward the chemical reaction, because there will have strong interaction when you will mix together and forward for the chemical reaction, because there will have different interaction like dipole-dipole interaction, hydrogel bond, and ion dipole interaction. So we will talk about this particular synthesis as our synthesis contains DMAPS, AA, and EMIMBR ionic liquid. When we will mix DMAPS, AA, and ionic liquid like EMIMBR, there will have interaction. You can see here nitrogen plus and oxygen minus. There is dipole-dipole interaction. And hydrogen bonding like acrylic acid have OH group, and here C double bond O have hydrogen bonding. And another also EMIMBr has positive side and DMAPS has negative side, oxygen minus. So there will have ion dipole interaction. So after forming this hydrogel, this can contains more amount of water due to ionic liquid have strong interaction with water, and it can contain more amount of water in order to make it stretchable, flexible, and more conductive. That I will discuss later how ionic liquid can perform more amount of ionic conductivity. Okay, this is the synthetic procedure of our pristine hydrogel. So you can say it our recipe or reaction ingredients. So this is the monomer DMAPS and AA. You can see here the full name, like AA is acrylic acid and DMAPS the full name. So we take monomer as DMAPS and AA, and you can see here the amount, like acrylic acid is the more amount and DMAPS is 0.654 gram, and we take PGDA as a cross linker to connect the polymer chain and bind to make it more rigid structure and robust structure. So here is the photo initiator. Photo initiator we take like 2559, and this reaction will be in nitrogen atmosphere. And why we take photo initiator? If we are taking photo initiator, then the photo initiator will decrease the reaction time and also decrease the energy. Also, this reaction is under the UV 365 nanometer UV light. So if you will put together and mix together and forward the reaction under 365 nanometer UV light for 30 minutes in nitrogen condition, so it will form like robust polymer network and it will form a hydrogel. Okay, next, the procedure for ionohydrogel. So procedure, what is the procedure for ionohydrogel? It's the same like before, pristine hydrogel, and just only the difference is to add EMIMBr inside in the reaction in the reactants. And here EMIMBr, the amount is 1050 milligram with DI water. So why we take DI water as the solvent? Because you know that DMAPS is a hygroscopic material. It has strong tendency to interact with water, because hygroscopic means loving towards water. So it will have strong miscibility with water. So we take water as a solvent for this reaction. Okay, then we will know about the mechanism of this hydrogel formation. So as this reaction will undergo an UV irradiation or UV treatment reaction, so we will know the what is UV reaction. Yet here you can see that HNU. HNU means photon bombardment. You can see the before, you know that like in acid base reaction or oxidation reduction reaction, when we will attack like negative or two electron, like on share pair electron will attack, so it will transport, two electron will transport. But in photochemical reaction, there will have transport of one electron, so we denote here like single arrow mark. But in acid base reaction or oxidation reduction reaction, we denote like full arrow mark, because two electron is transport, but here one electron will transport. Here you can see that when HP will bombard to the photoinitiator, because photoinitiator, when first HB will bombard, the photoinitiator will be active. So first process is photoinitiator will be active. This will divide to one electron this side and one electron this side. Here you can see the benzylic radical and 3-degree alcohol radical. If we will compare the reactivity between benzyl radical and 3-degree alcohol radical, the reactivity of benzyl radical is more. Then it will further proceed for the reaction. If uh, benzyl radical will see another vinyl group or any other group, so it will react vinyl group in the process of addition reaction. If there will have any negative charge or lone pair of electron, so it will attack to this vinyl group, and this vinyl group will shift this carbon atom, so it will be minus, but it is radical reaction. So this radical will attack here and this one bond will separate, so it will form a secondary radical. So also DMAPS have also vinyl group. Like this, benzyl radical will attack vinyl group like this way and form a 3 degree radical. You can see here the photo like cross linker have two side vinyl group, so it can also react two side. This one side is left side, one side is right side. You can see here first this molecule will form, and after again react this molecule will form. Okay, after forming three radical, this will form a robust 3D like 3D polymer like structure. This is we call hydrogel that contains more amount of water, which to in order to make it stretchable and flexible. You can see here before UV irradiation liquid, the molecule are separate, and after UV irradiation is adhesive that hardens when UV to exposed to UV light. You can see this picture that it's flexible and contains so many water inside in order to make it flexible and stretchable. Okay, if we are synthesizing some molecule, then the first characterization we can perform the FTIR spectroscopy, because it's the basic one. You can know easily our structure is successfully synthesized or not. Before going to FTIR spectroscopy of this particular hydrogel, then we will know about the basic principle of FTIR spectroscopy. The basic principle, the basic fundamental equation for FTIR spectroscopy is equal to nu is equal to c by lambda, where nu is equal to frequency and c is equal to speed of light, like 3 into 10 to the power 8 meter per second, or 3 into 10 to the power 10 centimeter per second, and lambda is equal to wavelength in centimeter. Okay, here in this picture you can see that when light source will come, this beam splitter is in 45-degree angle, it will split the beam, and then it will recombine and come to the sample cell, and then the beam will come detector, and we can see the like signal in computer screen. Then we will analyze our data in particular signal, like which centimeter inverse to in corresponding to which peak. Okay, this is the FTIR spectra of our pristine hydrogel. Here, the first black line is acrylic acid and red line is DMAPS. Then after forming hydrogel is the blue line. Okay, first we will go to the acrylic acid bond, which assignment is double bond CH bending, and the wave number is 980 centimeter inverse. You can see here is the acrylic acid, there is a peak, and also in DMAPS there is also a peak, but after forming polymerization there the peak is vanishes, which strongly suggests that after double bond polymerization the hydrogel is successfully synthesized. Then also we can go to another evidence of our hydrogel synthesis, that like 302 centimeter inverse, which correspond to Cn plus of DMAPS. You can see here Cn plus bond in hydrogel, there is an intense peak and it vanishes after forming hydrogel, which also another evidence of a polymer formation. And another also C double bond C stretching in 635 centimeter inverse of both acrylic acid and DMAPS. You can see here there is just intense peak in acrylic acid, also in DMAPS, but it is slightly reduced, or you can say vanish after polymerization reaction. That evidence has confirmed that our hydrogel successfully synthesized. Okay, then we will go to FTIR spectra of ionohydrogel synthesis. Here, the spectra of the black one is the spectra of EMIMBr. This is the ionic liquid spectra of EMIMBr, and red line is like pristine hydrogel, and blue line is ionohydrogel. Okay, so you can see here EMIMBr spectra 622 centimeter inverse corresponds to imidazolium cation or bromine anion. Here you can see that here in AMIMBr peak, but here in pristine hydrogel there is no peak. But if you look at the blue line, there is a little bit peak in corresponds to 622 nanometer, which strongly suggests that our ionohydrogel contains EMIMBr ionic liquid. And also CN stretching in 1569 nanometer, you can see that there is small peak also obtained in the ionohydrogel for C double bond and stretching. Then we will come for 635 centimeter inverse, which corresponds to also C double bond and stretching. We also observe in case of ionohydrogel in 635 nanometer. Okay, then we will talk about the ionic conductivity. Then before going to ionic conductivity, we will know that what is ionic conductivity. Ionic conductivity is the electrical conductivity due to the motion of ionic charge. Here you can see that first monomer and water and ionic liquid. After polymerization, it will form this is 3D robust like polymer chain, and also there are different positive and negative charge which increase the ionic conductivity due to increase the motion of ionic charges, but it's slightly different from electrical conductivity. But electrical conductivity also observed in metals and semiconductors, which defined as the moment of charge in response to an electrical field. The basic equation for ionic conductivity to measure is, if I write sigma as ionic conductivity, then the equation with length by resistance into area, where sigma is equal to ionic conductivity and R is resistance, L is thickness, and A is the contact area. If your conductivity will increase, your resistance will decrease, and area of cross section will decrease. So how to measure ionic conductivity? This is the instrument to measure ionic conductivity, that is EIS, electrochemical impedance spectroscopy. You can put your hydrogel middle, and upside is cathode or downside is anode, or you can put downside is anode or upside is cathode, like a sandwich structure. Then you can measure your ionic conductivity. Then we will go to the measurement of ionic conductivity by EIS. Okay, this is the measurement of our ionohydrogel conductivity. So we incorporate we will incorporate 5 weight percent, 15 weight percent, and 25 weight percent, 35 weight percent, and 45 weight percent ionic liquid inside into the hydrogel synthesis. Then we observe that up to 35 weight percent ionic liquid increase. Then after that ionic conductance increase. After that more addition of ionic liquid, ionic conductivity decrease. Then why we observe more addition of ionic liquid decrease the ionic conductivity? More addition of ionic liquid will decrease the water content, and also more addition of ionic liquid, there will formation of more amount of ionic charge which will aggregate together. Then if there will aggregate together, their motion will be slow, so that ionic conductance will be slow on addition of more amount of ionic liquid. Okay, then we will go to the mechanical properties of hydrogel, that is stress and strain. Before going to stress and strain, we will know about what is stress and strain. So you see here is the original position of hydrogel. This guy is stretching the hydrogel to become this position. So what is stress? To from its original position to another position, how much force you are needing, that is stress. Here you can see stress is the force applied to the material divided by material cross section area, that is sigma is equal to F by A0, where sigma is equal to stress. We can the unit is Newton per meter square or Pascal. Force is you can denote as Newton, and A0 is equal to cross sectional area. Here the pristine hydrogel have here the first position of hydrogel cross sectional area is low, but after stretching the cross sectional area is wider. And how much force you need to transform this hydrogel into another position? Also, this guy is stretching the hydrogel into like the longer size. Then come to the strain. What is strain? So how much length change from pristine position to another position? How much length you change? This is strain. Strain is the deformation or displacement of the material result from an applied force stress. If strain is epsilon, then L minus L0 by L0. L0 is the L is the length after load applied. Like here, if you will say that this is L means after load applied, this is the length is increased, means this is L. L0 is what? L0 is the first, the pristine position of hydrogel, which is L0. So L minus L0 by L0. Here you can see its strength is unitless because length by length is called length and length diminish. This is unitless. So we denote it as in percentage. Then go to the then we will go to the measurement of our hydrogel stress and strain. This is the measurement procedure of our hydrogel. You can see this is our pristine hydrogel, and we will see the measurement procedure of our hydrogel stress. This look at this video how stress and strain can be measured. Okay, so you can see this. This is the first position of hydrogel. Then is certain position. Then if we will stretch it in the certain position, it will break. So this is the maximum stress you can apply to the hydrogel. Then after that, it will break. So from this instrument, we calculate stress and strain for our hydrogel and iono hydrogel. Let's go to see the result. So this is the stress and strain measurement of our ionohydrogel. So we also observe same trend in case of 0 weight%, in case of stress and strain. So this is the 0 weight% means pristine hydrogel stress and 5 weight%, 15 weight%, 25 weight%, and 35 weight%. So here you can see that in 45 weight% the stress and strain also decrease. So why it decrease? Because ion aggregate and weak intermolecular force between ionic liquid and hydrogel. That's why stress and strain decrease after more addition of ionic liquid. Here is the representation of stress and strain in one graph. Okay, then we also test our hydrogel thermal properties and anti-freezing property. So how we measure our hydrogel thermal property and anti-freezing property? So by DSC, we measure our hydrogel thermal property and anti-freezing property. Before going to know our thermal property and anti-freezing property, we will briefly talk about what is differential calorie scanning calorimetry or DSC. So there are different terminology for the DSC, reference sample and sample. This one is reference sample holder. This is sample holder, and this is heat sink and thermocouple. DSC gives many signal like exotherm, endotherm, and glass transition temperature. So the basic principle of DSC is DSC heat flow or heat flow out of the system or into the system, like exothermic or endothermic process. Okay, let's see our result of our thermal properties. Here you can see that this is the red one is 35% EMIMBr incorporated hydrogel, that is ionohydrogel, and the black one is 0 weight% EMIMBr, that is pristine hydrogel. Here you can see that intense endothermic peak, that is crystallization temperature at 33.51 degree, and in case of ionohydrogel we didn't see in any peak in this region. Why? There is strong interaction between ionic liquid and water. This form a strong hydrogen bonding in case of ionic liquid and in case of ionohydrogel. So there is excellent thermal stability in this region. And but in pristine hydrogel, there is not that much hydrogen bonding as compared to ionic liquid. So we got this endothermic peak in at 133.51 degrees centigrade. We also test our ionohydrogel anti-freezing property like DSC thermal properties like 0 to positive temperature. Anti-freezing means 0 to negative temperature. Okay, this is the anti-freezing properties of ionohydrogel. Here, the black line is 0 weight% EMI/MBR and the red line is 35 weight% EMI/MBR. Here you can see an intense exothermic peak in minus 59.95 degrees centigrade, and due to strong hydrogen bonding, the peak diminishes and become smaller, like and observed at minus 78.42 degree for ionohydrogel. Okay, this is our ionohydrogel based TENG device. We take ionohydrogel as electrode layer, and we take PDMS as encapsulation layer. So why we take encapsulation layer? Because if you will take encapsulation layer, it will like uh, uh, inhibit the moisture intrusion or protect your device to degradation or this kind of thing. Also, what is the why we take PDMS as encapsulation layer? Because it's high electronegativity and good elasticity and transparent and prevent hydrogel dehydration and degradation. And you can, if you will see the PDMS layer, it's like white color and it is very much transparent. And this is the structure of ionohydrogel. It is cage-like structure and interaction with ionic liquid. It also acts as a electrode layer, and PDMS as a triboelectric layer. Also, our skin also acts as a triboelectric positive layer. Then we perform this TENG and know the device performance of TENG. Before going to device performance of TENG, we will know about the power density, because power density is the important parameter to know the performance of TENG. So what is power density? Power density can be defined as quantity of electrical power per unit area, that is P by A, where P is the contact area, and if we will define power is equal to V square by R, where V is the output voltage and R is resistance. The unit of power density is equal to watt per meter square. Okay, this is the output performance of our ionohydrogel based TENG. You can see that first, this is the pristine hydrogel, and after incorporating ionohydrogel, the current and voltage also increases. You can look at the value. The voltage is 23.6 volt and current is 3.3 for pristine hydrogel. After incorporating 35 weight% ionic liquid, we increase our voltage 60.4 and current is 7.2. Also, we observe the power density is 0.3 watt per meter square. We also compare our result with different literature. You can see the power density value from other literature, and our value is 0.32. That is comparable with other literature value. Okay, ionohydrogel based TENG also serve as a motion detecting ability or motion detection sensor. So here you can see this guy have different motion like bending, tapping, walking, and holding and clapping. So different motion can get different signal. Here you can see this picture, the 3x speed and 5x speed. 3x speed can get the lower signal, and 5x speed can get the higher signal. Here you can see another motion detection. Here you can see the slow detection and high detection. Here you can see the releasing and bending and different signal. If you will perform different signal, TENG will give you another signal in case of your different body motion. Also, this TENG can work as a biomechanical energy harvester. Okay, let's see this video how TENG can get the elbow joint motion after your body motion. Okay. In the next video, we will see that how TENG can act as a biomechanical energy harvester for mechanical sensing. So here you can see that Here you can see that the guy is tapping in his finger, and we can get the LED lighting, that is biomechanical energy. So we also test our ionohydrogel based TENG for different body movement like finger pressing, hand tapping, and hand gripping. You can see the different signal obtained by different body motion like finger pressing, different signal, hand tapping, different signal, and hand gripping is different signal. Our ionohydrogel based TENG also able to harvest low frequency biomechanical energy from different human body motion. Okay, let's see our video how we perform like finger tapping, finger pressing, like this or different body motion. You can see that different body motion have we are getting like in this figure. You can see if you will compare three figure, you can see that different body motion or finger tapping or hand gripping, you can get different signal in case of different body motion. You will if you will compare three signal, the three signal looks like different. Okay, let's see another video looking at talking about another motion of our hand. This is the elbow joint motion, the wider signal. Okay, then we come to conclusion. Our after incorporating ionic liquid EMIMBR, we get high value of output performance of TENG device. That is voltage is 60.4 voltage and current is 7.2 microampere, and the power density reached up to 0.32 watt per meter square. Also, this iono-hydrogel based TENG can also get different signal in order to in different body motion, finger tapping, hand pressing, and other body motions. Also, in future, this iono-hydrogel based TENG can act as a biomechanical energy harvesting and motion detecting and soft robotics. And also, it can help in Internet of Things or health management or other wearable intelligent electronics. Okay, thank you very much for listening. Thank you very much.